Okay, we want to talk about galvanic cells now. This is what a galvanic cell looks like. You guys have probably made one of these, or at least seen one of them in your general chemistry class either in high school or college. So a couple things you have to look out for. One, the salt bridge. It always is the first thing I look at. This just is like a tube, I guess you can think of. It has like plugs, so not everything can get through, and it just allows the flow of ions between the two beakers. Then you have this liquid in both beakers, the solution, right? In this one, there's copper nitrate. This one, there's silver nitrate, right? It's just a solution that contains some kind of metal ion, right? Which is like, in this case, it's the copper 2+, and here it's the Ag1+. The anode and the cathode, which are extremely important. It's just a stick of copper and a stick of Ag in the water. And one of them, the anode is negatively charged, the cathode is positively charged, right? Okay, but we're gonna talk more about this in words just to make it clear. So we talked about redox reactions, and the way a galvanic cell works is it takes a chemical reaction, which is this redox reaction, this transfer of electrons, and it uses this chemical reaction to actually produce electrical output, right? It's produce electricity, and that's what's read on top of this voltmeter, right? Just like when you have maybe a chemical reaction, when we talk about thermodynamics, you have a chemical reaction that produces energy, it produces joules. Some chemical reactions, these redox reactions actually, with the flow of electrons, they can produce a current, a voltage, right? Just like a normal chemical reaction can produce energy, right, or heat. So we can actually use this type of cell to make electricity for ourselves, okay? Using this redox reaction. An important acronym or mnemonic or whatever to know is RED-CAT and ANOX. This is extremely important. Reduction always happens at the cathode, and oxidation always happens at the anode. So before we had this full reaction that we broke into half reactions. Well, now we're actually separating out this half reaction physically. So if you notice, the anode is here and the cathode is here. Well, we're separating, so oxidation happens here in this tube, and then reduction happens right here in this tube, right? We're splitting the two half reactions physically by location now, okay? And it always follows this rule. Reduction always happens at the cathode. Anode is always the site of oxidation. Use RED-CAT, reduction, cathode, ANOX, anode, oxidation. Remember that the anode and cathode are pure elements, so they're in their atomic form, they're in their neutral form, right? In the solution, the metals are charged, they're ions, right? So just like we had here, if you see in the solution, it's copper 2+ and Ag+, whereas in this stick, it's Ag, and in this stick, it's copper, right? Just regular copper. And you can actually see this happening. So the copper is 0. In the stick, you can see with this arrow is becoming copper 2+, right? It's going from neutral charge to a positive charge, meaning it's losing electrons, meaning it's oxidation at the anode, right? So you're actually taking copper from the stick and putting it into the solution, and you're charging it. And then you also have this on the other side, on the cathode, you're actually taking this charged Ag, and you're actually turning it into just uncharged Ag in its elemental form, and you're going from a positive to a neutral. Going from positive to neutral means you're gaining an electron, meaning it's reduction. Reduction at the cathode, oxidation at the anode. Can't stress that enough. That'll help you with a lot of questions regarding galvanic cells. Now let's talk about the electrical output. Each reduction oxidation reaction, half reaction, creates a certain amount of electrical output, just like most reactions have a thermodynamic output in joules, like I mentioned before. We can use known values of separate reduction reactions and combine them to find the total electrical output of a cell. And I'll give you an example here. So we know, and this isn't using metals, which is what we usually use, but it's a good example that I found. So we have this O2 neutral, so it's neutral. going into 2H2O plus, right? And you're using these electrons, right? These 4 electrons. So this is by convention, we always write the reduction reaction when we're giving this, right? We never write the oxidation reaction. We always write the reduction reaction, even if it itself is an oxidation reaction. It's kind of weird, but you'll see exactly what I mean. So this is a reduction because you're getting electrons, right? And it produces a current of this many volts. When this reaction occurs, it produces this many volts of energy, right? Or not energy, of electricity. Then you have the Cl2 again plus, so it's again reduction. Goes in Cl minus, you're producing this voltage, right? But we know that for a galvanic cell, we have to have both a reduction and an oxidation reaction. We can't just have 2 reduction reactions, right? So how would we make this galvanic cell if we were to? Well, we know that the purpose of a galvanic cell is to essentially create as much voltage as possible, right? If we want to create as much voltage as possible, we want to use the reduction reaction that will generate the most voltage, and we want to use the oxidation reaction that will create less voltage in its reduction form. And I'll give you an example. This Cl2 creates more voltage than this reduction reaction. This Cl2 creates more voltage than this reduction reaction of O2. So if we were to make a galvanic cell using just these 2 elements, we would use this Cl2 as the reduction, right? We would use this as the cathode. And this we would use as the anode, because even though it does produce a current, a voltage when we make a cell, it doesn't produce as much as when we use Cl2 as reduction. And we know one of them has to be oxidation, right? We have to make one of them the oxidation. Well, so we would just have to flip it, right? If we were going to use this as the oxidation, the O2, we would just have to flip it. So instead of going this way, we're now going this way. We instead start off with water and we go towards the left, or if you want to, you can just flip all the elements that way. To get an oxidation reaction, we start with the water and then we oxidize water to make O2, right? Instead of reducing O2 to make water, we oxidize water to make O2. How would this change the electric potential? Well, it would just simply negate it. So electric potential is now negative 1.23, right? To go forwards is 1.23. To go backwards is negative 1.23, right? If we were to make a galvanic cell using these 2, this anode and this cathode, right? Using these 2 reactions, all we would have to do to find the total voltage produced by this cell is we would just have to add these 2 together, right? So we just have to add the 1.36 with the negative 1.23. You may see in some you may see you take the E standard of the reduction minus the E standard of the oxidation. You use subtraction without negating it. So what I did was I flipped it and I negated it to make it negative, and then I added. In some textbooks, you may see take this positive number, keep this as the way it is as a positive number, and then just subtract it. I don't like doing that. I think it's more confusing. I think it's easier to do it this way. Just flip it and then negate it. Makes it easier for me, but up to you. Just don't forget, if you do it my way, you have to add. If you do it like the way some textbooks or some books may say, you have to subtract. But yeah, keep that in mind. And when you add these 2, negative 1.23 and 1.36, you just get a total of 0.13 volts. And that's the total voltage produced by this cell if we use this as the anode and the cathode. As you can see, this is not a very good anode. This is not a very good cathode. These aren't very good. 0.13 volts is a very small amount. That's why it's not used. If you had, for example, a number that was already negative. So for example, if we pretended that this reaction, there are some metals that are like this, where the reaction itself, the reduction reaction, is already a negative voltage. So again, we want to flip it to go towards the left instead of the right. And we would still be negating the sign. So we would actually be making it positive, and then we would still be adding it, right? Now we have 2.59 volts. If we were pretending instead of oxygen, this was like reduction of lithium, it's like negative 1.23 initially. Then when you flip it to make it go towards the left, it becomes positive. And then you would add it, because after negation, you always add. And then you get 2.59, right, volts. And that's a lot. And that's what a good galvanic cell looks like. A good galvanic cell looks like. Okay. But in this case, you would negate, when you would negate it, it becomes negative, and then you add it and it becomes smaller. Another thing I want to point out, and that's important is, and that they will often trick you up on, is notice how there's 2 electrons here and 4 electrons here. When you flip it, and you flipped it already, there's 2 on the left, and then there's 4 on the right. So you actually do have to multiply this by 2. So this cancels out, and then this is actually 4, right? So you think, based on what you know from thermodynamics, that you multiply this by 2, right? Because it's you multiply the voltage by 2, but no, you actually don't do that. In galvanic cells, you don't care what the coefficients are. Like, even if you scale it, so like here they ask you write the balanced equation, so you would have to write the balanced equation, and you would have to recognize that, but it wouldn't change the E values, right? It wouldn't change the E values. The E value is still exactly the same. It doesn't matter if you multiply this by 2, by 10, by 100, the E value doesn't change. I want to talk about quickly why it doesn't matter what the coefficient is, and an important equation that you guys may encounter. It's not as common on the MCAT, but in case I do want to teach you, it's called the Nernst equation. For E, and it's delta G equals negative NFE. F is a constant. I believe it's Faraday's constant. I'm not even going to give you the value for it or anything like that, because there's no way they're going to ask you to remember it. They'll always give it to you, right? So there's no point in even memorizing it. It's like some ridiculous number that there's no way you're going to remember. But it's a constant. It's always the same. N is moles, right? And this is if they give you, say, E and N, and they want you to find delta G, you would use this Nernst equation. For our purposes right now, we're going to be trying to figure out how this relates with E. So we want to rearrange this so E is isolated on its own. And E is this E, by the way. E equals negative, if we isolate it, rearrange it, E equals negative delta G over NF. We know that when we double the coefficient, delta G does double as well. It's exactly proportional. So if we were to go from CL, this has like a delta G of, say, 10 or whatever, or like negative 10. And then if we double this, now the delta G is higher. It's like negative 20. So you actually would, and this is like what we expect, right? And that's why you would expect E to change. But if you notice, you multiplied delta G by 2, but N is moles, right? And the moles have also doubled, just like delta G. So while delta G has doubled in the numerator, moles in the denominator has increased by the same amount, has doubled, right? That cancels out, and that's why E remains the same. So if you double the coefficient, delta G doubles, but N also doubles in the denominator, and then they cancel out. Ultimately, E doesn't change; it stays the same, right? And that's important. Okay. And this question is much simpler than the last one. I know the last one might have scared you guys, but this one's a lot simpler. It's much more straightforward, and I think you guys will be able to figure this one out. Okay, last chance. Okay. Okay, so I'm happy. The majority of you picked C, which I'm happy about, right? And it is the correct answer. And I'm glad that the majority of you guys at least gave it a shot. Even if the answer wasn't completely right, it's okay. We're here to learn, and I'll go over this, and hopefully you guys will be able to understand it. Okay, so we know that this is the reaction that they give us. So you don't even really have to find which one is being reduced, like which one is being reduced or which one is being oxidized. They actually tell you. So this is good on this part. But we're given the reduction potentials for PB and Na plus. Like I mentioned, some of them are negative, right? Just like I said before. What you do is this one stays the same because it's being reduced here in the half reaction. It's being reduced in the actual reaction. Just keep it the same. Don't touch it. This one is being reduced in the half reaction, but it's being oxidized in the real reaction. So what all you simply have to do is negate it. And you just make it positive. Now, once you do that, all you have to do is just add these two numbers together. When you add negative 0.13 and positive 2.71, you get C. Some trap answers, D. The way you would get D is you would look at this coefficient, 2 times Na, right? The reason you would think that is, well, if there's 2 Na, so obviously you would multiply this by 2, so that means this would be multiplied by 2 as well, right? That's what you may think. But like I mentioned, with electric potential, never do that. That's always the wrong answer. And that's every time they give you a question like this, they'll always have that as an option because they want to trip you up, because that's how it is for thermodynamics, and for delta H, delta G, delta S, that's how it is. For this is not how it is. For voltage, that's not how it is. For voltage, doesn't matter what the coefficient is, it always stays the same. Okay, and I explained why that was, and it's due to the Nernst equation, right? Okay, why is A not the answer? So B, I'm glad nobody picked, and honestly, you could have kind of found A, narrowed down to A or C before, but why is it not A? Well, this is because this is being reduced in the half reaction. Look, this is a PB2 plus 2E is PB. This is being reduced in the half reaction, and then in the real reaction, it's also like that. So you don't have to touch it because it's already in the form you want it to be in. This one is in a different form, right? Because here it's NaS, and on this side it's Na plus. Whereas here it's on the left side is Na plus, the right side is NaS. So in order to correct it, you would have to actually switch the arrows around. If you switch the arrows around, you have to negate. Right, and I'm going to erase that. You have to negate. Negative turns to positive, and you get positive 2.71. Right. Now, let's pretend that they didn't give you this. Right. If they asked you to figure that out on your own. Right. Pretend that they didn't give you that. How would you determine which one is being reduced and which one is being oxidized? Well, you know that the one, what this number means, essentially, you want to think firstly, what does this number actually mean? What this number means is, when I do this reduction reaction, how much electricity am I making from doing this reaction? As you can see, from this one, you're actually not making any, you're actually losing a little bit. For this one, you're losing a lot of electricity, right? If you were to perform this reduction reaction, you were gonna lose a lot of electricity. You'd have to actually pump in electricity, right? What you want is you want to have the reduction be the highest number, right? In terms of like a number line, the highest number, the one that's most to the right. This number is higher than 0.13 is higher than negative 0.13 is higher than negative 2.7. So you want to use this as the reduction, right? Because it's higher, right? It's closer to positive. Okay, if you use this as for a reduction, the other one has to be used for oxidation. There's no other way. You have to have one oxidation, one reduction. You can't have both reduction, you can't have both oxidation. So then what you would have to do is you would have to use this one for oxidation, and that means this one is going to be the one that gets flipped. Right? And that's it. And then you could just get this full reaction from that. Because you would keep the PB from here, from this left side, the Pb2 plus. Because you flip the arrows, now the NaS, the Na like neutral is on the left side because the arrows are flipped. Again, you have to multiply by 2 because there's 2 electrons here, only 1 here, so you have to multiply this whole equation by 2, and then you just get PBS, this one on this side, plus, okay, we're almost done. I just wanted to quickly mention electrolytic cells before we wrap up for today, and then I'll take questions at the end, any problems you guys have. Electrolytic cells are the opposite of galvanic cells. While a galvanic cell, I mentioned, it uses a redox reaction to create an electrical output, to create a voltage, and that's what we've been looking for. We've been looking for the reaction that has the highest, that creates the highest voltage. An electrolytic cell is exactly the opposite. An electrolytic cell is you actually are using a battery. You're using electricity to make a reaction happen. Instead of using a reaction to make electricity, you're using electricity that you already have to make a reaction that wouldn't normally happen, right? One important difference is the sign of delta G of the reaction. So for example, all the reactions we've been talking about for galvanic cells, they have a delta G of a negative delta G, meaning they happen spontaneously or they'll happen on their own. And because they happen spontaneously and on their own, they produce electricity, right? Whereas in an electrolytic cell, the reactions have a positive delta G, meaning that they won't naturally happen. They won't happen on their own. That's why you need to actually take a battery or any other electric source of electricity. You actually need to pump electricity into the reaction in order for it to happen. You need to add something in yourself for the reaction to happen. Another difference is the sign of the anode cathode. Like I mentioned before here, in a galvanic cell, the cathode is positive over here, positively charged. The anode is negatively charged. In a electrolytic cell, it's the opposite. If you can see here, the anode is positively charged, the cathode is negatively charged. Really, I wouldn't suggest like putting too much emphasis on memorizing like the cathode anode signs. It's kind of important, but it's rarely tested. I think like the actual signs itself, if you don't have it memorized, it's not too big a deal. If you have like the spacing, I guess, in your mind that you are not using for something more important, memorize it. It can't hurt, but it's not like too important, but just know it's different. Electrolytic cells, as you can see here, they don't use a salt bridge like they do here. They happen in one beaker, whereas in galvanic cells, there are 2 beakers connected by a salt bridge. Instead, electrolytic cells use a battery as a source of electricity. So if you can see here, and when we cover circuits, we'll talk, this is the sign for a battery, right? So you need to hook up a battery, otherwise this won't work. And the battery sends electricity into the cathode and like this in a circle. Whereas in a galvanic cell, since you didn't need to put in electricity, you're actually making electricity. The only thing they might have, and this isn't a requirement for galvanic cells, but most have it, is a voltmeter, which just measures the amount of voltage going through. Over here, it just measures how much electricity is being produced. Whereas in a electrolytic cell, you have to make the electricity to put in. In an electrolytic cell, positive charge on the anode and negative on the cathode, which I mentioned, while in a galvanic is reversed. Red cat and anox still apply, by the way. Even though the signs of the cathode and the anode are flipped, reduction always happens at the cathode no matter what. Oxidation always happens at the anode no matter what, right? It doesn't matter, it's just the signs of the actual sticks are flipped. Oh yeah, and you asked that in the chat, yes. Reduction always at the cathode, oxidation always at the anode. Red cat, anox is always applicable. Same thing as oil rig. Oil rig, where they're talking about electrons or H+, oil rig applies. Oxidation is loss, reduction is gain. That's about it. I want to talk about maybe quickly about the purpose. And this is the last slide, by the way. So if you guys want, you guys are free to go after this. But the purpose of electrolytic cell versus galvanic cell. Galvanic cell is usually if you wanna make a battery. a battery is just a galvanic cell, right? Essentially, you take, or modern batteries, not so much, but classic batteries, like old batteries, are essentially just galvanic cells. You have copper, and you have an anode and a cathode. Usually it's copper, and I think they use palladium or something like that. I don't remember what it was for the cathode or whatever. And you just create this, and it creates a big current, and that's how you from using a chemical reaction, you make electricity, right? That you can store, and that's how you make. That's what a battery is. It's just a storage of electricity. And whereas in an electrolytic cell, you already have a battery, you already have a source of electricity, but you want to make a reaction that doesn't normally happen. That's more for chemistry or biology. You would use an electrolytic cell, whereas if you're going for practicality in real life, like a battery or something, you would use a galvanic cell. For electrolytic cell, if there's say a really like tough reaction that never happens in nature, it's very hard to get to happen. Sometimes it's a redox reaction. It has to be a redox reaction, right? You can sometimes force it to happen just by putting in some extra voltage into the system, right? And it will get the reaction going.